I'll be recording this. Hemanga now he has come. It should be on time. So I straight away go for the share button. Microsoft PowerPoint carbohydrate. This is what is there. Do you see this slide? Hello, some of you respond.
Yes, sir.
Yes, sir.
Okay. So this was the slide.
Yes, sir. Yes, sir.
Okay. All right. Now you keep your keep mute. Microphone you keep mute. Whenever I ask something from you, you just unmute and respond. All right. So I straight away go to this slide. We had discussed this slide last time. Carbohydrate, what is the definition, how they are classified. This ultimately we come to the monosaccharide. Monosaccharide is made up of two types. One is aldoses, another is ketoses. Ketoses we have not discussed here, but ketoses I'll ask you to write down all the different classes of ketoses with their names and structures. Later on, I'll give it in the Google Classroom question. So aldotriose, aldotetrose, aldopentose, aldohexose. Now what we find here, now you see people are coming and asking for joining now. This disturbs this classroom. We find that aldotriose, aldotetrose, aldopentose, aldohexose. So we go to the next slide. We quickly pass on to this classification. Already we have done it. I go to the next. Now, configuration of monosaccharide. This is what is our discussion today. Configuration of monosaccharide. Now, what we have seen that monosaccharide, aldoses or ketoses, they are aldoses or ketoses. Somebody asking for joining here. Noor has come now. Now, what we see here, what do you mean by configuration? Configuration, what happened? Oh, now configuration, what we find here, what do you mean by configuration? Configuration is, now you see, this is what is the problem. People come and ask for the joining later on. Configuration, now you see. Configuration of a molecule is a relative arrangement of atoms and groups around the chiral center if it is an optical isomer, or around the rigid structure in case of geometrical isomers. Already we know what are this configuration. That means the arrangement of atoms and groups. Arrangement of atoms and groups around that chiral center in this case, because all these are optical isomers. But how many chiral centers we get here? Now this is what we got last time. From the monosaccharide, what we find? We have got aldoses and ketoses. Ketoses we are not discussing. We have got aldotriose, tetrose, pentose, hexose. Now, aldotetrose has got one chiral center. Aldotetrose has got tetrose has got two chiral centers. Aldopentose has got Aldopentose has got three chiral centers, and hexose has got four chiral centers. And accordingly, we have got this is what is the problem. Number of optical isomers. Aldotriose will have 2, tetrose will have 4, pentose will have 8, and hexose will have 16. What is this 2 means? There are 2 configurations for aldotriose because of one chiral center. Tetrose will have 4 configurations, means 4 different arrangements of atoms and groups around these 2 chiral centers. So for aldopentose it will be 8 and aldohexose will be 60. Now let us come to the next slide. Now aldotetrose, so we start with aldotriose. Aldotriose, how many? We have got one chiral center, so there is two structures. Now these structures that we are writing here will be all in the Fischer projection. Fischer projection means structures and horizontal and vertical lines. That is Fischer projection. Already you know. And these trios are named glyceraldehyde. So there are 2 of structures. One is your here I am not writing H here. H will be on the other side of this carbon. This is the carbon junction. H will be on the other side. I am not writing H just to minimize the crowding. It is understood that there is H on the other side, on the left hand side in this structure and the right hand side in this structure. So these 2 aldotriose will have 2 isomers. That means one, this is the chiral center, the middle carbon atom. So around this chiral center, CHO on the top and CH2OH if we write on the bottom, this H and OH can be having the position right hand side or left hand side, OH position. Now, you know that any carbohydrate, any optical isomers will be either dextrorotatory or levorotatory. And if it is meso compound, it will not be dextro or levo, it will be optically inactive. Now, how do you know that this is positive here? Positive means what? This is positive means it is dextrorotatory, and negative means levorotatory. Can you tell me why we have written this? Is there any? Okay, they get disconnected and again joined. Okay, we have got 37%. All right, can you tell one of you just unmute your mic and tell me why this is going to be dextro and this structure is going to be levo? Anybody? We have done our yes. Anybody?
Dextrorotatory means clockwise rotation.
No, okay, but why this particular structure is dextro? Why this particular structure is dextro? I think you must remember your first semester class. We cannot predict the rotation from the structure. We must know it experimentally. When this structure is taken, its experimental determination of specific rotation shows that it is dextrorotatory. And
configuration is R.
Configuration is R doesn't mean that all R structures will be dextro. It can be levo also. So here this is an experimental observation that is there. that is which is dextro, so we write plus, and this structure, the molecule with this structure is LIGO, so we write minus. Now configuration is something different and optical rotation is something different. Don't confuse optical rotation and configuration. Optical rotation is the experimental observation, is an experimental observation. Now, so aldotriose had only one chiral center, so there will be two isomers, and these are the two structures. And this structure with the OH group on the right hand side in the Fischer projection is found to be dextrorotatory, so it is plus, and this is found to be levorotatory, so it is minus. Okay. Now, after that we go to aldotetrose. See, this is giving trouble. Aldotetrose. So aldotetrose means, already we know it had three chiral centers, so there will be four structures, four isomers, four optical isomers, or four configurations. Now, how do we write these four configurations? These four structures will be something like this. Just see. Two structures will write from here, and two structures we write from here. When we write down the structures from here, what we have to see? That this particular OH group which is there, it is on the right hand side in both of them. Okay? And the new structure that is formed will have two different arrangement. For one, the first one will write OH on the right hand side. For next one, we'll write OH on the left hand side. Remember, for first structure, we write on the right hand side. For next structure, we write on the left hand side. Similarly here, this one, we find this part is coming from here. This remains same in both of them. Both of them, it remains same. For first structure here, we are writing on the left hand side, and next one we'll write on the right hand side. But okay, we can use the same methodology that is there. First structure which I will write on the right hand side. In that case, we should have written it here, and this one we should have written it here. And their names are like this. This is erythrose and threose. And this erythrose is found to be levorotatory. Now see here, this was dextrorotatory. You can say that these are the two children out of this glyceraldehyde, this particular molecule, two children born from here. What is the identity of the parent? The parent will, whatever this part of the parent is remaining same in both of them. What is changing here in the new chiral center, where we'll write this OH on the right hand side and the next OH on the left hand side. But you find here this is plus glyceraldehyde, but this has become minus erythrose. This is also minus threose. So this minus is experimental observation. So experimentally, when the experiment is carried out with this molecule, we find it is levorotatory, so we write minus here, and this is also minus. But here, this is erythrose, which is the mirror image of this one. So erythrose, but it is plus erythrose, and this is plus threose. This is just see the mirror image. So the names are also kept as erythrose and threose. So these are the four configurations of aldotetrose, four aldotetrose. One is minus erythrose, minus threose, plus erythrose, plus threose. Now when we go to the next aldot, and the next will be your, what will be the next? Aldopentose. How many Aldopentose structures we must have. How many configurations in aldopentose? Anybody respond?
9.
8.
9.
9.
8. 8.
8.
Sorry, sir.
Already we have seen. But how this 8
Two chiral
will
center.
yes, 3 chiral centers, so
Two
that will
chiral.
be 8. Now,
Yes.
how these 8
Two.
structures will come? Remember, 2 will come from here, 2 come from here, 2 come from here, 2 come from here. When I say 2 come from here, means what? These 2 will have this part of the molecule remain same in both of them. This part of the molecule will remain same in both of them. And when 2 come from here, that means this part remains same in both of them. So what we find here, this is not working properly. This aldotetrose, 8 isomers, and this 8 isomers will be like this just now. I am not writing all of them. This part I am not writing anymore. Now here, just see, erythrose will give rise to these 2 structures. What was the similarity here? This part, you see, this part is already here. Just see, this part is already here. Both of them are same. But the new chiral center that is there, the first one OH on the right hand side, next one OH on the left hand side. And from trios, another 2 comes where these 2 will have this part of the molecule. The old one will remain same in both of them. Just see, this they are same. And the first one, the new chiral center, first one will write OH on the right hand side, OH on the right hand side, and OH on the left hand side. So there, so these are 4. Another 4 will come from here. Just see, 2 from here, another 2. So I am not writing, otherwise this will become too crowded and you will get confused. You can write using the same methodology. And what is their names? These 4 structures: ribose, arabinose, xylose, lysose. But ribose, you find here, this ribose is having another 10 minutes left. We have to disconnect and again continue. This ribose is negative, arabinose is negative, but xylose is positive, lysose is negative. Now, this positive negative, as I say, you cannot predict from the structure. It is an experimental observation. Remember that. This is where most of people commit a mistake or have got very little understanding. So what we find here, this ribose, arabinose, xylose, lysose, only 4 I take. Next I ask you one question. I have given this line. Line is dividing, is a boundary line. Huh? Now you see, I'm telling you one fact about, say, when if you, now imagine, come down to something like a family structure. Family structure. If I consider glyceraldehyde to be the original great-grandfather, then this plus glyceraldehyde, where this OH group is on the right hand side, minus glyceraldehyde, which OH group is on the left hand side, they are giving rise to their offsprings, the future generation. The future, this one gives 2, so this one give rise to 2, and this one give rise to another 2. Then comes this one, in turn will give 2, this one will give into another 2. Then in turn, this one will give 2, this one will give 2, this one will give 2, this one will give 2. And so also here. Now, as the family becomes too big, what happens? They get separated, and there is a boundary wall already get created. The people say that okay, we are from this particular grandfather, great grandfather, and they are from another great grandfather. So they get separated, and the boundary wall is created. But if you find this particular group, what is the similarity in the how? What is the similarity in all these structure? Can anybody tell? And what is the similarity in all those structures here? Anybody tell? What is the similarity of all these structures that we have here? And what is the similarity of all these structures that is there? Can anybody tell? Come on.
All
Sorry,
OS
first,
group.
the bottom one, the bottom OS group in all the molecules here, we have in right side.
Who is
For the
telling? No,
first,
no. Your
sir,
name. Who is
sir,
telling?
Samim,
Shamin.
sir.
Shamin
Yes,
Nasrin.
sir.
Okay.
Yes, sir.
And what about this one?
For this one, all the molecules will get the bottom OS in the left side.
Bottom chiral center, the OH group
Yes,
on the left hand side.
left side. Yes, sir.
All of you do, yes, this is the answer. You find this is the genetic strain, you can say. Okay, this is not the right term to be used as gene. This is not gene, nothing to do with gene here. But okay, if we go to family members, so they keep this identity of their great grandparent. This part you find here, all of them are there on the right hand side. Yes or no? And this one will have, this group will have this OH group, is this, the first chiral center from which it started is on the left hand side. So they are identified by two different clans, two different groups of molecules. So ultimately two different configuration, and this configuration are given the symbol capital D and capital L. So what we find here, this one you see here, this one, this capital D comes before their name, and this one will have a capital L in front of their name. This capital D and capital L does not signify that it is dextro or devo. It tells about the configuration of the D-glyceraldehyde, where this OH group is on the right hand side and this one with this OH group on the left hand side. So all those structures obtained from this will be given D configuration. So these two also get D and D. So this is D minus erythrose and D minus threose. This D is that showing that it is related to D minus glyceraldehyde, and this, sorry, D plus glyceraldehyde, and this D is showing that it is related to D plus glyceraldehyde. But the optical rotation of this compound is minus. Remember, optical rotation, and this D telling that this is the OH group is on the right, this OH group in the right, and this one. So also here, these structures will get L configurations, L. And so aldopentose, when we come, 8 isomers will have, in the 8 isomer, this 4 will be D and another 4 will be L. So what we find here, this D, so it is D minus ribose, D minus arabinose, D minus like xylose, and D minus like so. And another 4 L configurations will be there, which I am not writing. You can write down from here. Got my point? Now, we are left with 2 minutes. Now, so I stop here. Again, you will rejoin. I stop here, I disconnect, and again you will rejoin. Stop sharing and end of this meeting. Leave meeting and meeting.